Hello. This is Nicholas, and today I wanted to talk about a problem from one of our homework assignments that was a little bit interesting and gave me a little bit of trouble at first, and then eventually I came to a good answer. It was on summing trig functions where the angles are an arithmetic progression. So the particular problem was to find a simple formula for sine squared theta plus sine squared 2 theta plus sine squared 3 theta, so on and so forth, up to sine squared n theta. And so this is not the most general case, obviously. The most general case would be something along the lines of sine squared. You would have a sum, say from k equals 1 to n, of sine squared of a, the first term, plus k minus 1 d, where d is that common difference, theta. And that would be the most general type of problem. But we'll see, though, that I'm not going to attack this because we're going to deal with our fair share of generality in the video. So, how would you come up with a formula for something like this, right? So the first thing that, pops out to me, well, I tried a number of things. For example, I tried setting s equal to the sum from k equals 1 to n of sine squared of k theta, right? That's just our original problem written in sigma notation. And then taking the derivative, so like s prime would be sigma k equals 1 to n of, and then here's where the problem arises, because you could bring the 2 up front, 2k sine k theta cosine k theta. And in this particular case now, sure, you can use the double angle identity, and then the 2 goes away, and then you'd have a k sine of 2k theta. And this would have been a lot better if this k wasn't here. And so in essence, we need to find a way to reduce, get rid of the squared term, because get rid of the squares on each one of those terms, because that really makes it a lot yuckier. I think it's pretty easy to see that. And then what else we need to do is some way so that we just have, say, a sine of theta plus a sine of 2 theta plus ... plus a sine of n theta, or a cosine of theta, cosine 2 theta, cosine 3 theta, so on and so forth, right? So what are we going to do? The thing that I thought to do was, we have identities for each one of these, power reducing identities for each one of these. And so that's what I'm going to use here to reduce the power, right? So I know that sine squared of theta is 1/2 times 1 minus cosine 2 theta. And this one you've probably used a lot in calculus, is usually where it pops up the most, when you're integrating sine or cosine to an even power, right? You can use this power reducing formula so many times and you'll get it down to just a single power, right? An exponent of 1. And so this is where that identity usually comes up, but we're going to use it here in this case, right? So to think of that, I guess you just kind of have to have it in your toolbox. So we're going to transform each one of these terms using that power reducing identity. So we're going to get 1/2, because each of them is going to have a factor of 1/2. And then for the first one, we're going to get 1 minus cosine 2 theta. And then for the second one, we're going to get 1 minus cosine of 2 times 2 theta, or 4 theta, plus ... plus 1 minus cosine of 2n theta. Yeah. And that's all going to be multiplied by that 1/2 out front. Now, we get 1/2 times, now there's n of these 1s, so we get n, and then minus, and I'm just going to pull the minus sign out front. We have cosine 2 theta plus cosine 4 theta, so on and so forth, plus cosine 2n theta. All right, and this is a lot nicer to deal with because now we have gotten rid of the square part, and we have also made it so that these angles inside form a very nice and succinct arithmetic progression. So now what we're going to consider is a formula for the sum of the cosines where the angle forms an arithmetic progression. So I'm going to just tackle the most general case here. The most general case would be the sum from k equals 1 to n of cosine, and I'm just going to write the theta in here once, and then I'm going to kind of get rid of it because it'll just make things look messy, and then I'm going to add it in back at the end. So just for the time being, know that it's there. So we're going to have cosine of a plus, say, k minus 1 d. And so this is why I don't want to add the theta in, because now I have to take all that, multiply that by the theta, you see, so it makes it look a little yucky. This is the most general case right here. And so this part that is being multiplied by the theta is the formula for the nth term of a geometric series, or a arithmetic series. And so that term in front of theta would therefore form an arithmetic progression. So now I'm just going to kind of ignore the theta. And what I'm going to do now is I'm going to go complex. So I'm going to use complex numbers, and Euler's formula are almost always very powerful tools to prove kind of these obscure trig formulas that you might not think of at first, without using kind of like standard elementary trig. It is almost always guaranteed to give you some sort of a solution. So what I'm going to do is I'm going to make this the sum still from k equals 1 to n. But what I'm going to do is I'm going to make this the real part, right? And I'll elaborate what this means in a second. And make this of the real part of e to the I times a plus k minus 1 d. And I'm not going to add the theta in here. I'll add it back in at the end, just for the sake of making it look a little nice. So what we mean by this is we mean the real part of whatever this is equal to. And recall from pre-calculus, and you can prove this using Taylor series in calculus, that e to the I theta is cosine theta plus I sine theta. And so we would therefore define the real part of, say, e to the I theta to just be cosine theta. And so it literally is just taking the real part, right, anything that doesn't have an I on it, of this expansion of e to the I theta. Likewise, we define what's called the imaginary part of e to the I theta to just be the sine of theta. And so it's just whatever has an I attached on it, right? We don't obviously include the I already because we know it's the imaginary part, and so therefore it's already going to have an I out in front of it to begin with. So that's just some notation that we're going to use here. Now, what else we can do is we can essentially take the real part outside of this sum. And so what that means is, because basically we'd be having a sum where we'd be taking the real part of each term. And so we'd just be getting all real parts. Or we could make it where we take the real part and then just keep the sum with the whole thing, right? In other words, do the sum, including real and complex or imaginary parts, and then just take the real part of that resulting sum. So I'm putting the real part out front now, and we have a sum from k equals 1 to n. And I'm going to make this e to the IA, e to the IA. That is awfully reminiscent. That might be something I should probably be doing instead of this math video. Anyways, e to the IA times e to the ID Oh, I wish this was idk, but it's k minus 1. That would have been kind of funny. Okay, so I just split up using basic exponent rules here. Now this is the real part of, and now I can actually pull this e to the ia out front of the sum, but still within the real part, because e to the ia does have a imaginary part, and so I can't pull it totally outside, but I can pull it outside of the sum, because the sum is only concerning k, right? And so things that are, using k need to stay inside of it, but things that are not using k are treated like constants with respect to k. So I'll pull this e to the ia out front. I'm going to get e to the id to the k minus 1. And now what I'm going to do is, let's see. I will make this e to the ia now. Oh, oops, still the real part. The real part of e to the ia times, now this is the whole crux of why we convert to complex here, is because this sum now is just a super nice geometric formula, right? It's just the sum of a finite geometric series. So recall, and this was actually one of the exercises like on the previous part, it was to show that 1 plus r squared plus ... plus r to the n is equal to 1 minus r, n minus 1 up there for the exponent is 1 minus r to the n over 1 minus r. And so we're going to use that fact right here, basically, because it's the same thing, right? Instead of r, we're just letting r equal e to the id. And so now we're just going to get a nice geometric series, and so that is going to evaluate to 1 minus e to the idn over 1 minus e to the id. Okay, and now what I'm going to do is I'm going to make this the real part of e to the ia, and I'm going to actually notice that this 1 is really e to the 0, right? And basically what I'm going to want, and it'll make sense kind of if you've seen the complex definitions for sine and cosine, and perhaps I should write them here. I guess I'll just derive them real quick. We know that e to the I theta is cosine theta plus I sine theta. And now if theta becomes negative theta, I have e to the negative theta, negative I theta, is cosine of negative theta. Cosine is even, so cosine of negative theta is still cosine of theta. And we have plus I times the sine of negative theta. Sine is odd, so the sine of negative theta is the negative of the sine of theta, and we get a minus I sine theta. And what you can do now is you can just add these together, and you would end up getting that e to the I theta plus e to the negative I theta all over 2 is equal to cosine theta. And if you were to subtract instead of add, you'd get that e to the I theta minus e to the negative I theta all over 2I is equal to sine theta. And so basically what I'm going to want is, I'm going to want, just to make it kind of nice on me, is I'm going to want each one of these like exponents here to have right here, to have the same magnitude, but just opposite in sign. Because if I get that, then I can just use this complex definition of sine and cosine, and it'll simplify things greatly. So in other words, what I want is, the only way I'm going to be able to turn this 0 and this idn to have the same magnitude but opposite in sign is by basically taking the arithmetic mean of those exponents. In other words, what I'm going to do is pull out an e to the idn over 2 and make this e to the negative idn over 2 minus e to the idn over 2. And now you see that those two exponents right there are the same magnitude but opposite in sign, and so we're going to be able to use this complex definition of sine because we have subtraction right there. That's how I remember it, by the way. Sine, you subtract. Anyway, and then I'm going to pull out an, on the bottom here, I'm going to pull out an e to the id over 2 and make that e to the negative id over 2 minus e to the id over 2. And this is all taking the real part of all this. So, hopefully I'm going to kind of make this as pretty as possible so that you can see it really clearly. But you should be able to kind of see it already, that this right here, this first part right here, is going to end up being sine of, I didn't write quick enough, sine of n d over 2 theta. And then this bottom part right here is going to be sine of d over 2 theta. But I'm going to write it more clearly so that you're able to see that. So we have the real part of e to the ia times e to the idn over 2 over e to the id over 2 times, now I'm going to be dividing this fraction here by a negative 2i on both the numerator and the denominator, so it doesn't change anything. So I get e to the negative idn over 2 minus e to the idn over 2 over negative 2i over e to the negative id over 2 minus e to the id over 2 over negative 2i. And then I'm going to make that negative sign here go away and change that to I'm going to negate the numerator of both right here. So in other words, I'll get the real part and still e to the ia, e to the idn over 2 over e to the id over 2 times, now we're going to have e to the positive idn over 2 minus e to the negative idn over 2 over 2i over e to the id over 2 minus e to the negative id over 2 over 2i. And now, so all I did to get from those two things was I just basically negated the numerator and negated the denominator of this whole big fraction right here. So within this part right here, I made that 2i, that negative 2i into a 2i, and then I just changed around the order of that part right up top, and did the same thing for this part down here on the bottom. Now, it should be super clear what these are going to become, right? This part right here is precisely, if you compare it with this definition up here, sine of n d over 2 theta. Right, and realize that the thetas are actually written in here. I just was lazy and didn't want to write them in because it makes the computations look yucky. Likewise, this part down here is, by looking at this formula up here, again, is the sine of d over 2 theta. And then this part right here, if we're considering just the real part, we're getting just cosine stuff, right? So if I kind of combine this together, I get e to the I times a plus n minus 1 d over 2, because I just added the a and this dn over 2, and then subtracted by another 1 because I'm dividing here, just exponent laws. So now this part right here, if we're taking just the real part of it, we're just going to get the cosine of what's inside right here. So what am I saying with all this is that this part, the real part of all of this yucky stuff, simply becomes cosine of, and now I'm going to add the thetas in. So I have a plus n minus 1 d over 2, right? And that's just coming right from here because we're taking the real part of that. Theta. So that's all being multiplied by the theta. Now we have the sine of n d theta over 2 over the sine of d theta over 2. And that right there is the formula for the sum of cosines of an arithmetic progression, where the angle, where the angles form an arithmetic progression. And maybe I guess a challenge for you would be to do the exact same thing, but to find that formula for sine. So in other words, sigma k equals 1 to n of sine of a plus k minus 1 d, and then this is all multiplied by theta. And it's literally the exact same thing, except instead of taking the real part here, remember that the e to the I theta was cosine theta plus I sine theta. And so now if you're talking about sines that form an arithmetic progression, you're going to want to be taking the imaginary part of the sum from k equals 1 to n of e to the I times a plus k minus 1d. And you do the exact same thing that we did up here. So just kind of a cool challenge for you. If you are able to do that, you probably get this. So now our particular sum that we were interested in was cosine of 2 theta plus cosine of 4 theta plus plus cosine of 2n theta. So namely, this is the case in the formula above that we derived where a is equal to d is equal to 2. Right? The first term is a 2 right here, and then it goes up by 2 each time. So that gives us that, or that tells us that this sum right here is just the same thing as cosine of now we have a 2, so 2 plus n minus 1 times d over 2, but that's 2 over 2, which is 1. So we're multiplying by a theta there. Then we have the sine of n theta, because d is equal to 2, and those 2's just cancel out, over the sine of theta. For the same reason, the d and the 2 cancel out, because d is 2. So simplifying once more, we have cosine of n plus 1 theta sine n theta over sine theta. And so that is that answer to this original sum right here. And so remember that we had 1/2 times n minus this whole sum right here. Well, that whole sum is the same thing as that right there. And so we can just replace it with that, right? So cosine of n plus 1 theta sine n theta over sine theta. And that right there is the formula for the sum of the sines of an arithmetic progression, right? In other words, sine squared of k theta. And it would be the exact same thing, except at the beginning where we use the identity that sine squared theta is equal to 1/2 times 1 minus cosine 2 theta. You would use a very similar identity, just if you're dealing with cosines now, you'd want to use the fact that cosine squared theta is equal to 1/2 times, oh, and I always have to derive this one. Cosine 2 theta is cosine squared theta minus sine squared theta. And then sine squared theta is the same thing as 1 minus cosine squared theta. So we get 2 cosine squared theta minus 1. Yeah, so it's going to give you 1 plus cosine 2 theta instead. So that minus sign just changes to a plus. And so then the only difference that you're going to have between the sum of squares of sines that form this nice arithmetic progression, namely where you just, increase by 1 with a starting point of 1. The only difference would be that this minus sign changes to a plus sign. Because all you're doing is instead taking the positive sum of all of those things, which we already found, rather than negating the whole thing. And so I hope this video has been helpful for you in proving these pretty nifty formulas. And I think with that,